class, we are going to learn how to name alkanes. Remember, I have uploaded the first two videos, the foundation on how to name alkanes. So if you did not watch the foundation part of this, you go back to the previous videos, you will see the title, How to Name Alkanes, Part 1. After watching Part 1, you come to Part 2. Now today we are looking at the Part 3, and we are using a skeletal structure. A skeletal structure is the structure where we choose only lines, only bonds. We don't show the carbons and hydrogens. Now in a skeletal structure, every junction represents a carbon atom. Here we have a carbon, here we have a carbon, we have a carbon here, we have a carbon. All the junctions, each of them represent the position of a carbon atom. Now we are asked to name this alkane. Remember the 4 rules I gave earlier on how to name alkanes. Rule number 1 says, identify the longest continuous carbon to carbon chain. So let's identify the longest chain here. The longest chain simply means the longest uninterrupted line. I can check here. This is a chain. This is another chain. There are different directions. This is another direction. This is also a direction. And this is also a direction. We also can move this way. So you can see the line did not cut. It is still this way. We can also check it this way. As long as there is no breaking of line, it is allowed. Now, if we check all the different directions, you'll notice that the longest direction you have here is from here. Okay, we'll have it like this. Our longest direction in this compound is from here to this place. Watch, if I count from here to here, I will have 1, 2, 3, 4, 5, 6, 7, 8, 9. If I count from here to this end, I will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let me check if I have any other direction that is longer than 10. For now, my maximum is 10. So let me check. If I move from here to here, I will have 1, 2, 3, 4, 5, 6, 7, 8, 9. If I move from here to here, I will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. I have seen something greater than 10, and that is this direction. From here, you move this way. The line is still continuous. It did not break. Still moving. This is my longest chain, 11. There is no other direction you get here that will be greater than 11. So our longest chain is from here down to here. And that is what rule number 1 says. Identify the longest continuous carbon to carbon chain. And I have done that, and I discovered that the longest chain is 11. And the 11th hydrocarbon, or the 11th alkane, is called undecayed. The 11th alkane is called undecayed. That is the alkane with 11 carbon atoms. So I have identified my longest chain, which is undecayed, 11. Now, the next thing, the rule number 2 says, identify the substituents or attachments present. Attachments are those carbon branches which are not part of your longest chain. Remember, our longest chain is from here to this place. This is our longest chain. This direction. This direction. This is our longest chain. This is our longest chain. So this is not part of the longest chain. This is not part of the longest chain. And this is not part of the longest chain. Now, how many carbon branches do we have which are not part of the chain? There are 3 of them. There are 3 carbon branches here, which are called attachments. Attachments are those carbon branches which are not part of the longest chain. I have them here, 1, 2, 3. Every other carbon here is part of my longest chain because this is my longest chain. Now, Inside this attachment, I have only one carbon, which is methyl. Inside this attachment, I have only one carbon also, which is methyl. But inside this attachment, I have two carbons, which is ethyl. Now I'm going to bring out the names. The next thing to do, which is rule number 3, after locating your attachments, rule number 3 says, number the carbon atoms in the longest chain, starting from the side that will give the attachments a lower number. So I'm going to assign numbers on the carbon atoms in my longest chain. If I number from this place, remember the longest chain has two ends, this place and this place. So it is either I number from here to here, or I will number from here to here. Let's check. If I number from here, I will have 1, 2, 3, 5, 6, 7, 8, 9, 10, 11. If I number the longest chain from this end, my attachments will be at position 4. That is, from this direction, I'll have the attachments at position. The first one is at position 4. The second one at position 8. The last one at position 9, which is 489. 489. Now, what if I number the attachments from this direction, from left to right? Let's see. Because the rule says number from the side that will give the attachments a lower number. Now if I start from here, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Remember, do not number the carbon atoms in the attachment. Number only the carbon atoms in the longest chain. So if I number from this direction, I will have my attachments at positions 3, 4, and 8. 3, this one is at position 3, this one is at position 4, and this one is at position 8, which is 348. So you can see 348 is lower than 489. The rule says number from the side that will give them a lower number. If I number from this side, it will be 489. From this side, 348. So I'll follow my left side where they will have a lower number. Now the next rule is rule number 4, which says when writing the name of the compound, write the positions and names of attachments first, followed by the name of longest chain. Let's see. This is my longest chain. Now the attachments I have ethyl at position 8, which is 8 ethyl. I also have methyl group. I have methyl group 2 places. One is at position 3, the other is at position 4. So I will say 3, 4. Because there are 2 of them, I will say dimethyl. Dimethyl. Methyl groups are positions 3 and 4. Now I'm going to compile these 3 names. The name of the longest chain, the name of this attachment, and these attachments. When writing the names, start with alphabetical order. The names of the attachments will be written first, while the name of the longest chain will be written last. Now, the attachments are ethyl and methyl. So E comes before M. The name becomes 8 ethyl. We write E before M. Then I have 3, 4 dimethyl. I have written the attachments. Then the next thing to write is the longest chain, which is undecayed. So the name of the compound is 8 ethyl 3, 4 dimethyl undecayed. And that is the answer. Let's quickly look at another example. After one more example, I'll give you one to try. After watching, you try the one I'll give you to try. We have something like this. Let's name this compound on the board. Rule number 1 says identify the longest continuous carbon chain. Our longest chain, if I take this direction, I will have 1, 2, 3, 4, 5. If I take this direction, I will have 1, 2, 3, 4, 5, 6, 7, 8. If I take this direction, I will have 1, 2, 3, 4, 5, 6, 7, 8, 9. If I take the horizontal direction, I will have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So my longest chain is the horizontal line, which is 10. And number 10 is called decay. So my longest chain is decay. So no matter what the name of this structure will be, it must end with decay. That's the rule of naming. The name of an organic compound ends with the name of the longest chain. So since my longest chain is 10, the name of this compound must end with decay. Okay, the next step is to identify the attachments present. Here are my attachments. Those carbon branches which are not part of my longest chain are called attachments. I have another attachment here. This one is 3 carbons here. This one is 2 carbons. And here I have another attachment as well. And this is 3 carbons. So I have attachments at 3 positions. Step 3 says number the carbon atoms in the longest chain, starting from the side that will give the attachments a lower number. Now my longest chain starts here and ends here. So I have 2 options. It's either I number from here and end here, or I will number from here and end here. One is correct. How do I know the correct one? If I number from here, I will have them at 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So numbering from left to right, my attachments will be at position 3, 5, and 7. 357. But if I number from right to left, let's see where the attachments will be. It will be 1, 2, 3, 4, 5, 6, 7, 8, 9. I think I skipped something. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now if I number from right to left, my attachments will be at position 4, 6, and 8. 468. And the rule says, follow the direction that will give the attachments a lower number. From this way, I have them at 357. While from this other side, 468. So this way is lower. I'm going to number from left to the right because it will give us a lower number. So we'll have it as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, now let's identify the names of these attachments. The attachment at position 3 has 2 carbons, and that is ethyl. This is 3-ethyl. The one at position 5 has 3 carbons, 1, 2, 3, which is propyl. The one at position 7 also has 3 carbons, but I'm not going to call it propyl because I'm noticing something. Note this. I have 2 propyl attachments here, but look at the difference between the two. This is propyl, this is propyl. If I number this propyl, 1, 2, 3. This one, 1, 2, 3. Look at the difference now. This one is connected to the big compound. This propyl is linked to the big compound from the first carbon. This one is connected, this is the longest chain. It is connected to the longest chain from the first carbon. As you can see, this first, second, third. First, second, third. So this is connected to the compound from the first carbon. In that case, we'll call it propyl. But here, it is connected to the compound from the second carbon, like this, from the second one. So whenever it is connected from the second carbon, we call it iso. Iso shows it is connected from the second. Then how many carbons are there? 1, 2, 3. isopropyl. Isopropyl. Assuming it is like this, assuming you have it like this, if you have it like this, where you have 1, 2, 3, 4 carbons, and it is connected from the second, you call it iso. Then how many carbons? 1, 2, 3, 4. Butyl. Iso. Iso means it is connected from the second. But when it is connected from the first, we don't put iso, just say butyl. Alright, so this one is connected from the second carbon. Therefore, the name is isopropyl. Now I have 3 methyl, I have 5 propyl, I have 7 isopropyl, and my longest chain is decay. How do I compile these names? You write the positions and names of these attachments first. When you are done writing the names and positions of the attachments, you now write the name of the longest chain. Now follow the attachments in the alphabetical order. The first is E. E comes first. After E, you have I. After I, you have P. Then the last is K. So this is 3 ethyl, 7 isopropyl, 5 propyl, decay. 3 ethyl, 7 isopropyl, 7 isopropyl, 5 propyl, then the longest chain is decay. And this is the name of the structure given. Alright, I'm going to give you one question to try by yourself. Let me see what you can do here. Now, do this as an assignment. Get me the name of the structure I'm going to draw on the board. When you discover the name, go to the comment box, type the name you got, and I will mark your answer. Now we have a structure like this. We have this. Okay, let's make it a little more spicy. Let's make it a little more spicy. This is the assignment. This is the assignment I have for you for today on this section of the class. Give me the name of this structure, write your answer in the comment section, and I will mark and get back to you. Thank you for watching this video. Please do not forget to like this video, drop a comment for us to encourage us, and please share this video with your friends. Do not forget to subscribe. Thank you for watching. Today we'll be looking at electrophiles. What are electrophiles? Electrophiles are substances which are electron deficient that can accept electron from an electron-rich substance. Now remember, electrophile simply means electro plus phile. In our philosophy, we call this philia, love. This is love. The full meaning of philia is love. Electro here simply stands for electron. That means an electrophile can also be called electron-loving substance. Electron-loving substance. Now, what can make you to love electron. Electron is negatively charged. A substance that will be in love with a negative charge should be a positive charge. Remember the law of nature, opposite charges attract. So for you to be in love with electron, which is a negative charge, it means you are a positive charge. So electrophiles are deficient of electron. They are lacking electron. So they will be attracted to a negative charge. That's why they are called electron-loving substances. And for them to be in love with the electron, it means they are lacking electron, so they will need to gain electron. Remember this, electrophiles are electron-loving substances which are deficient in what? Electron, and are capable of accepting electron from an electron-rich substance. Examples of electrophiles at this level are the Lewis acids. Lewis acids are good examples of electrophiles. And Lewis acids we have at this level are copper 2 ion, hydrogen ion, which you call the proton, aluminum trichloride, and boron trichloride. We can use only these four. There are many others. So these are examples of Lewis acids. And Lewis acids are good examples of electrophiles. Remember, they are electron deficient. Electrophiles, one of the things you use to know most of them is that they usually carry positive charges to show that they are lacking electron. Somebody that is positively charged is someone that lost electron. And when you lose electron, you are lacking electron. You are electron deficient. So they are usually positive charges to show that they are lacking electron. They have lost electron. So these are electrophiles. Though we still have neutral compounds that can be called electrophiles, just like aluminum chloride and boron chloride. If I draw the structure of this, you will see what makes it an electrophile. But let me use this rough sketch to show you. In aluminum trichloride, this one, aluminum is the central atom, while we have 3 chlorines surrounding it like this. Now, if I draw this, you discover that nothing is here. In this shell of aluminum, the outermost shell of aluminum has 3 electrons here. Now, 3 chlorines are to be bonded to it. One of the chlorines will stay here, the other chlorine stays here, the other chlorine stays here. Nothing is here. So this place is lacking electron. We can use this as an evidence to show that this is an electrophile because it is electron deficient. There is no electron here. The same applies to this. Don't forget this. Electrophiles are electron deficient substances which are capable of accepting electron from an electron rich substance. When electron is donated to them by a substance that has more electron, they are ready to accept. In the next video, we are going to explain the meaning and examples of nucleophiles. Thank you for watching, and don't forget to please share with your friends and subscribe. The question says, use the data above to determine the following. Number 1, the reaction order with respect to hydrogen. Number 2, the reaction order with respect to iodine. And number 3, the overall order of the reaction. Now let us solve this problem. The data is on the board as you can see, and the reactants used there, the substances used in the reaction are hydrogen and iodine. So I'm going to write my Rate's law equation. And remember, the Rate's law equation says that rate is equal to rate constant K times concentration. So I'll write it on the board here, which says that rate is equal to rate constant multiplied by concentration. Here, the concentration I'm going to use will be 2. The one from iodine and the one for hydrogen. So I have my hydrogen here, multiplied by iodine here. Now, I do not know the order of the reaction with respect to hydrogen and with respect to iodine. I am going to find them. That is why the data on the table here is given to us. So because we do not know the power, we are going to represent the exponents as x and y. That means we are going to find the values of x and y. I know that the order of reaction with respect to hydrogen here is equal to x, while the order of the reaction with respect to iodine is equal to y. And the overall order of the reaction is equal to x plus y. So all we need to do is to find the value of x, find the value of y. Okay, now how do we start? Now, this table shows that this experiment or the reaction between hydrogen and iodine was carried out in 3 different sections. The first experiment is the one called experiment 1. In the experiment 1, 0.031 molarity of hydrogen was mixed with 0.054 molarity of iodine, and the initial rate was discovered to be 4.920 times 10 to the minus 4. After that, the experiment was repeated again, which is experiment 2, and this were mixed, and this was the observed initial rate. The third experiment was carried out, this and this were mixed, and we got this rate. Now with this, we can find the values of x and y. I'm going to substitute rates and concentrations for me to be able to find x and y. Now I can decide if I want to find x. If I want to find x, I will look for 2 values where y will cancel out, because we cannot find x if we do not know y, and we cannot find y if we do not know x. You cannot have 2 unknown at the same time. So if I want to find x first, I will have to look for where the values of y will cancel out. Now how do I do this? I should know that I can call this experiment 1, which means this is my R1. I can call this my R2. I can call this my R3. Okay, now if I say R1 divided by R2, that is initial rate, the first one over the second one, I will have R1 all over R2 will be equal to, if I'm doing this over this, it means that I will do this over this. But if I do this over this, then I will do this over this. How do I go about it? My R1, I chose this as my R1, which is 4.920 times 10 raised to the power minus 4, all over my R2, which I chose to be this. Remember, this is a rate. So this is my rate 1, this is my rate 2, which is 1.476 times 10 raised to the power minus 3. If I do this over this, it will be equal to this over this. So it will give me this times this, which is 0.031 times, this is concentration. I will multiply with this 0.054. That's 0.054. Divided by, I did this over this, so I'm doing this over this. Remember, it is rate equals concentration of H times concentration of I. This is concentration of H, this is concentration of iodine. So if I do rate 1 over rate 2, I will do concentrations 1 over concentrations 2. I know that my K will cancel out, so I'm not bringing in K. Even if I bring it in, it will still cancel out. Okay, now the second one, which is this 0.093 all multiplied by 0.054. Now, with this, I can now put their powers. Remember, my H, my concentration for hydrogen, bears power X, while iodine bears Y. This is my H. This is my iodine. This is my H. This is my iodine. So here is H, which is X. Here is iodine, which is Y. Here is H as well, which is X. That is X. And this one is my iodine, 0.054, which is power Y. Now, if you look at this, you will discover that 0.054 power Y will cancel 0.054 power Y. So this will cancel out. Now that my Y is out, I can comfortably find X. How do I do that? If I press 4.920 times 10 power minus 4 divided by this, I will get this over this will give me 3. That is 1 all over 3. Am I correct? Equal to, if I divide this, I will have here as 0.031 power X, all divided by 0.093 power X. All I need to do now is to find my X. How do I find this X? I will look for a way to split this bigger value here. I'll break it into 2 so that something can cancel out. How do I do that? I will say 1 all over 3 is equal to 0.031 raised to power X divided by 0.093 is the same thing as 3 times 0.031 all raised to power X. Remember, I've not done anything. This 0.093 is the same as 3 times 0.031. I looked for the number that will use and multiply this, so it will give me this. When I found that number, I discovered that 3 times this thing will give me this. So I brought out 3 and this. So this thing here is the same as this. So I've not changed anything. And this simply means that 1 all over 3 is equal to 0.031 raised to power X divided by 3 power X times 0.031 power X. You can now see that this will cancel this. And by the time they cancel out, I'm going to have here that 1 all over 3, 1 divided by 3 is equal to, I've cancelled out here, I have 1 left up, divided by 3 raised to power X. This is what I have. If I invert this, it means that 3 divided by 1 is equal to, this one goes up, 3x over 1. So this is what I have. Therefore, simply means that 3 is equal to 3 raised to power X. And if 3 power 1 is equal to 3 power X, remember the power here now is 1. Simply means that 3 raised to power 1 is equal to 3 raised to power X. Therefore, my X is equal to 1. Remember, this thing simply means 3 power 1 equals 3 power X, because the power here is 1. If I equate the basis, I'll have it that X is equal to 1. That's what I have there. I have gotten the value of my X. I can now find the value of Y. Let us proceed to finding the value of Y. How do we find Y? The same method. I will look for the 2 values that can eliminate X so that I'll find Y. Let's do that again. We can now take, remember, X is for iodine. X is for hydrogen. Y is for iodine.
Action.
Alright, we are now going to find the value of Y. We have found our X and we got 1. Now we are going to find Y. And for us to find Y, we are going to look for the values of x that will cancel out. That is, we'll choose where x will have equal values and choose where y will not have equal values. Remember, hydrogen bears our x. Remember, we are working with rates. Equals rate constant times hydrogen concentration times iodine concentration. And our hydrogen has power of x, while our iodine has power of y. So in order to find y, we will eliminate x. How do we eliminate x? X is the one of hydrogen. We are going to look for two values of x that will cancel out, and that is this and this. So we are going to use this and this so that this divided by this will cancel out. You can see we can now be able to find y. Y is for iodine, x is for hydrogen. So here, this and this are equal. So we use these two values, which means we also use here and we also use here. So I can use this and this now. I can say 4 points. If I like, I can say this over this, or I'll say this over this. Anyone you like, you are correct. But if you are using this over this, you must use this over this. But if you are doing this over this, you must do this over this. So let's try this method. Let's use this divided by this. This over this. That means my rate 1 point, this is rate. My first rate, which is 1.476 times 10 raised to the power minus 3, divided by the second rate here, that is the third rate, 4.920 times 10 raised to the power minus 4. Here, sorry, this is minus 4, is equal to the rate constant multiplied by the concentrations. The rate constant will cancel out, so no need showing it here. I have my two concentrations, hydrogen concentration and iodine concentration. Hydrogen concentration and iodine concentration. Remember, for this rate, this is concentration of hydrogen, this is concentration of iodine. For this rate, this is concentration of hydrogen, this is concentration of iodine. So for this rate, which is this is my hydrogen concentration, which is 0.093, and this is my iodine concentration, 0.054. I'll put the respective powers. Hydrogen has my power of x, iodine has power of y. Now for this rate, which is this is my hydrogen concentration, 0.093. This is my iodine concentration, which is 0.018. Hydrogen has power of x, iodine has power of y. So as you can see here, the x will cancel out because they are equal. And I have this over this, which will give me, if I punch this divided by this, then I will have 3 all over 1. That's what it will give me. Equal to, I have 0.054 left. All raised to the power of y. Raised to the power of y. Divided by 0.018 raised to the power of y. So I have to find the value of y. Just as we did earlier, all we need to do now is very simple. What do we have to do? All we have to do is, what are we going to use and multiply the lower value to get this higher value? If I find the number that will multiply 0.018 to get 0.054, I will use that number and split with this in order to be able to cancel one of them. So how do? I know that 3 multiplied by 0.018 will give me 0.054. So I'm going to eliminate 0.054. That means I'm going to have this, which is 3 all over 1 is equal to, this thing here is the same thing as 3 times 0.018, all raised to the power of y. Both raised to the power of y. I have not done anything. This power y is this power y here. This 0.054 is the same thing as 3 times 0.018. I looked for a number that will multiply this lower one to get this. And as soon as I got that number, I used the two of them to replace this. Now divided by this one under here, 0.018 raised to the power of y. And according to indices, if I have AB raised to power 2, is the same thing as A power 2 times B power 2. So I'm going to open these brackets. I have 3 and this. If I open up, I will have 3 power y times 0.018 power y. So what I will get will now be 3 divided by 1 is equal to, opening this bracket will give me 3 raised to the power y multiplied by 0.018 raised to the power of y, all divided by 0.018 to the power of y. So you can see this can cancel out. So I have with me here 3 over 1 is equal to 3y. I can still say over 1. From here, you can simply see that we have gotten the value of y as well. And from there you have 3 is equal to 3y. And what is the power of this 3 here? It is 1. Therefore, my y is equal to 1. I have gotten the values of x and y. In summary, my x is 1 and my y is also 1. Remember, 3 here, the power is 1. This is 3 raised to the power y is equal to 3 power y. So y is 1. Now, I have gotten x is 1 and y is 1. I can now answer the question. And those questions, question number 1 says, find the order of the reaction with respect to hydrogen. I can find it. Now, my rate, let me rewrite the equation. My rate, which is equal to rate constant times hydrogen raised to power x and iodine raised to power y, simply means that now that I have the values of x and y, I can rewrite it by saying that rate is now equal to K times hydrogen to the power of x, which is 1, times iodine to the power of y, which is also 1. So, number 1 question, we are going to answer it. Number 2 and number 3. The first question there says, what is the order of the reaction with respect to hydrogen? With respect to hydrogen, as you can see, the order is 1, and 1 simply means first order, which is first order. Number 2 question says, what is the order of the reaction with respect to iodine? With respect to iodine, the order is also 1, which is first order as well. And number 3 question says, find the overall order. The overall order is the sum of the orders. I have the overall as 1 plus 1. That gives me 2. And 2 here means second order. Overall order is second order. And that is the answer. Thank you for watching. In the next video, I'm going to still give one more example of this. Welcome to today's class. Today we'll be looking at the reactions of alkanes. Let's see some of the reactions alkanes undergo. At first, we need to take a look at an alkane, like methane. If we have methane, which is the first member of the alkane family, we need to know the type of reaction alkanes generally undergo. Looking at this alkane, which is methane, you can see that all the 4 bonds of carbon atom have hydrogen atoms attached to them. Remember, in organic chemistry, every carbon atom present in an organic compound must have a total of 4 bonds attached to it. In this alkane, we have the 4 bonds as 1, 2, 3, 4. That is the lines represent the bonds. In some cases, you can have it as 1, 2, 3, 4. In that case, there will be nothing here. In some other cases, you can have the 4 bonds as 1, 2, 3, 4. In some cases, it can also be like this: 1, 2, 3, 4. what you should know is that 4 bonds must surround every carbon atom. It can be in this form, it can be in this form, it can be in this form, and it can be in this form. It's a total of 4 bonds all around the carbon. Now, we are looking at the alkanes, the ones that have single bonds. You can see that the 4 sides of the carbon, something is up, something is down, something is in front, and something is at the back. The carbon atom is said to be completely saturated with hydrogens. Now, for a new substance to come to this carbon, let's take for instance, I am bringing an element called X to react with this alkane. You should know that there is no vacant space for this X to come and attach itself to this carbon. The only way this X can attach to the carbon here in an alkane is to knock out one of the hydrogen atoms in that alkane and replace its position. And a situation where the incoming person replaces an existing atom in the carbon atom is called substitution reaction. Removing someone and replacing that person with a new person, such a reaction is known as what? Substitution reaction. Alkanes generally undergo substitution reaction because they are completely saturated. Assuming you have a compound that is not saturated, something like this, you discover that in this compound, this place is vacant. This place is also vacant. So any incoming person has a place to stay. It can stay here. In that case, we don't need to remove a H before bringing in that person. This one is addition. A new substance can add. But in this case, there is no vacant space. All the 4 sides are occupied. So before a new person can stay, the old existing person needs to go for the new person to stay. Such type is called substitution reaction. But when a new person comes and stays without anybody leaving, that one is called addition reaction. Now, you should know that because alkanes are completely saturated, alkanes undergo substitution reaction. Remember, alkanes are not very reactive. Because they are completely saturated, they don't easily react. They are almost inert. And that is why they are known as paraffins. Alkanes are also known as paraffins. And the term paraffin means little affinity. Little affinity. They are not easily attracted to other compounds because they are completely saturated. But under severe conditions, they can react. And some of the reactions alkanes undergo, the first reaction here we'll look at is halogenation reaction. The number 1 reaction of alkanes we'll be looking at here is halogenation of alkanes. And what is halogenation? Halogenation is the addition of a halogen. When a halogen reacts with an alkane, that reaction is called halogenation reaction. Halogenation, halogen. Now, let's take methane for instance. If I have methane, which is CH4, reacting with a halogen, such as chlorine for instance, if I have chlorine molecule reacting with methane in the presence of ultraviolet light, UV means ultraviolet. Remember, the reaction between an alkane and halogens can only take place in the presence of ultraviolet light. Without ultraviolet light, alkanes cannot react with halogens. This simply means that alkanes do not react with halogens in the dark. In the absence of light, they cannot react. But in the presence of light, they can react. Now, what happens here is that the 4 hydrogen atoms present in this methane, this is what exactly happens, is reacting with the 2 chloride or chlorine radicals here. This will split into 2. There will be a bond cleavage, homolytic bond cleavage. In the previous video, go back to the previous videos, you will see the topic I treated earlier known as bond breaking. And one of the types of bond breaking is called homolytic bond breaking. You will understand why we have free radicals here. Now, when this chlorine molecule splits into two, we'll have them as free radicals. The first chlorine radical comes to the halogen, picks out one of the hydrogen atoms. The first chloride radical will pick this hydrogen, forming HCl with it. Now, after picking out this hydrogen, a vacant space is created for the second chlorine radical to replace. In that case, you now have it like this. That is CH3Cl. CH3Cl plus HCl. So you can see that the reaction between an alkane and a halogen produces a haloalkane and HCl. What is a haloalkane? A haloalkane is a compound that is made up of a halogen and an alkane, an alkyl group. This is haloalkane. If I want to call the full name, I will call it chloromethane, or I will call it methyl chloride. Either I call it methyl chloride or I will call it chloromethane. See what happens here? The two atoms of the halogen coming to react with this alkane, this is what happens. The first atom will pick one of the hydrogens from the alkane and form HCl with it, while the remaining chloride radical will replace the position of that H that was removed. If I remove one H here, I will have CH3. Now, the second chlorine will replace that position where the first chlorine was removed from. You now have CH3Cl. So the reaction between a halogen and an alkane produces a haloalkane. This is chloromethane, while this is methane. In summary, when chlorine reacts with methane, we produce chloromethane. If bromine reacts with methane, we produce bromomethane. There is one important note you need to take here in this reaction. When the chlorine is in excess, if I'm reacting with excess chlorine, let's take for instance, during the reaction, the chlorine we are using is in excess, while the alkane, that is the methane, is not in excess. All the hydrogen atoms in that methane will be replaced. Take note. When the halogen is in excess, the hydrogen atoms present in the methane, all of them, the four of them will be replaced. So in that case, you'll be having, if I remove the four hydrogen atoms and replace with four chlorine atoms, I will have CCl4. And this is called, this is Cl. This is called tetrachloromethane. Methane because it's one carbon. Tetrachloro because there are four chlorine atoms. So this is called tetrachloromethane. Note this. We replace all the hydrogen atoms in the methane when the halogen is in excess. But when the methane is the one in excess, if I have the methane to be in excess, something like this, when the methane is in excess, not the halogen, only one of the hydrogens will be replaced. When the methane is in excess, only one H will be substituted. But when the halogen is in excess, all the hydrogens will be substituted. So in this case, only one hydrogen will be substituted. If I remove one H here, I will have 3H left. Now, one H I removed will combine with one of the chloride radicals here to give me HCl. While the remaining chlorine here will replace the position of that H that was removed, giving us Cl. So, when the methane is in excess, we form chloromethane. Only one chlorine will be there. But when the chlorine is in excess, we form tetrachloromethane. That is the reaction between halogen and methane. That is our case. Now, another important thing you need to know about halogenation of alkanes is this. Halogenation reaction of alkanes take place in 3 stages. There are 3 stages of halogenation. Those 3 stages are step 1, initiation stage. Initiation stage. You can call this stage 1. Stage 1 is called initiation stage. What exactly is initiation stage? Remember, we are talking about the stages of halogenation. Before a halogen can react with an alkane, 3 things happen. There are 3 steps the reaction passes through before the product is formed. Those steps are what we call stages of halogenation. The stage 1 is called the initiation stage. What happens at the initiation stage? The initiation stage is the stage in which the halogen molecule splits into 2 homolytically. This is what we mean. The chlorine molecule, in the presence of ultraviolet light, breaks up into free radicals this way. Remember, the dot here represents unpaired electron. In a chlorine molecule, where you have a bond between 2 chlorine atoms, in this case, every bond is formed using 2 electrons. And because this is chlorine and this is chlorine, they both have equal electronegativity. So none can take the 2 electrons to itself, because they are both electronegative and they have equal strength. So this one will go with 1 electron, this one will go with the other 1 electron. So the dots here represent the electrons. So these are called free radicals. Free radicals. This simply means that free radicals are formed at the initiation stage. I repeat, the first step of halogenation is the stage in which free radicals are produced from the halogen molecule. The halogen will split into 2 with the help of ultraviolet light, forming what we call free radicals. That is what we call initiation stage. Even if you are using bromine or iodine molecule, for instance, 2 atoms of the iodine will break up into 2 in the presence of ultraviolet light, giving us iodine radicals like this. These are called free radicals. Now, the summary of initiation stage is that the initiation stage is the stage in which the halogen molecule is broken up into free radicals using ultraviolet light. The ultraviolet light is the catalyst used in halogenation reaction, and the function of the ultraviolet light is to enhance the breaking or the formation of free radicals. It is the ultraviolet light that breaks the halogen molecule into free radicals. Now let's quickly go to step 2. After the formation of the free radicals, which is step 1, let's see what happens next. The step 2 is called the propagation stage. Propagation stage. What happens at the propagation stage? It's simple. At the propagation stage, the free radical produced will start attacking the alkane. Remember, the halogen molecule does not just go and attack the alkane like that. No. The halogen molecule will first split into 2, which is into free radicals. One of the radicals will go and attack the alkane. This is the alkane, which we used methane as an example here. Now, the first out of the 2 free radicals we produced, we have 2 of them here. The first one will go and attack the alkane. This is the first radical. It will come to attack the alkane. Attacking the alkane means knocking out one of the hydrogen atoms. So one of the hydrogen atoms here will bond with the free radical here. giving us HCl. Now there will be a vacant space created here. We'll now have CH3 radical. This is what happens at the propagation stage. I repeat, the first stage is the stage where free radicals are formed using ultraviolet light. The second stage is called the propagation stage. And what happens at the propagation stage is that one of the free radicals produced, one of them, will attack the alkane you are using and pick one hydrogen atom from there, forming HCl with it. The alkane will be lacking one hydrogen, as you can see. Instead of CH4, we now have CH3, because the first free radical that came to attack picked one of the H and formed the HCl with it. Now, the last stage, which is stage 3, is what we call the termination stage. The last stage is called the termination stage. That is the stage in which the reaction comes to an end. The termination stage is the stage which the halogenation reaction comes to a halt. It stops. What exactly happens is that the methyl radical that was formed during the propagation stage, the one whose H was knocked out, will combine with the second halogen radical. Remember, there are two halogen radicals. The first one went to the alkane and pulled out one hydrogen. Now the second radical will come and take the position of that H that was knocked out. You now have CH3Cl. And at this point, the reaction stops. Remember, the first stage is called the initiation stage, and at initiation stage, free radicals are produced using ultraviolet light. The second stage is called the propagation stage, and at the propagation stage, one of the free radicals produced will attack the alkane and pick one of the hydrogen atoms from the alkane, forming HCl and methyl radical. The third stage is the stage we call the termination stage. What happens at the termination stage is that the remaining free radical, the remaining one, will go and take the position of that H that was knocked out from the alkane, giving us a chloroalkane. Those are the 3 stages of halogenation.